Welcome to AQA, A-Level Physics, Measurements and Their Errors, Use of SI Units and Their Prefixes. Let's go over SI units first. SI units is an international system of units, so wherever you are in the world you'll be using those system of units, much like the binomial system of naming things of genus and species in biology. Now SI units comes from the French System International de Units, or however you say that in French, meaning International System of Units, and you can see where we get SI from. Now there's 7 base units. Base units are what we measure. These make up all the other units. These are as follows. Mass, measured in kilograms. Distance or length, measured in meters. Time, which is measured in seconds. Electric current, which is measured in amps. There's temperature, which is measured in Kelvin. There's also the amount of something measured in moles. Those are the 6 you have to know for A level. There is one more I put down, which is the 7th of the International System of Base Units, which is light intensity, measured in candela, shortened to CD. You don't need to know much about it apart from it's the 7th. It exists. Let's go back over these. Mass, kilograms, distance, meters, time, seconds, current, amps. You would have been familiar with that. As well as amount, mole. That's more chemistry, but still is a base unit. Temperature is in Kelvin. Kelvin's an absolute scale. That's why we use it. It is so 0 Kelvin is equal to minus 273.15 degrees Celsius. And then that's the coldest you can possibly get, and then it increments at the same rate. So 1 Kelvin, if you plus 1 Kelvin, it's the same as plus 1 degree Celsius. And we use Kelvin to measure temperature. Now, you may be thinking, well, what about newtons? What about joules? They're units, they're not on here. Yeah, they're what we call derived units. They're made up of these 7 base units. Let's have a look at force in newtons. Newton's second law, F equals ma. Mass is measured in kilograms, one of our base units. Acceleration is measured in meters a second to the minus 2, which is composed of 2 more base units. So that's all in base units, and that gives rise and creates the Newton. And because this is inconvenient to write, we just Newton force. Force is the same as kilograms times meters times seconds to the minus 2, but we just say newtons. Newtons is a derived unit, it comes from these. We can look at another example. Kinetic energy in a substance, or say in a substance, but in something. Mass, measured in kilograms. Velocity, meters times seconds to the minus 1, but because we're squaring it, that's meter squared and multiplied by seconds to the minus 2, and that then creates the joule, another derived unit, which is much simpler to write than that. And this, yeah. Now, the joule isn't the only unit of energy. There is 2 more you have to know. There is, I'll get a different pen to make this distinct. Let's write it up here. Electron volts and kilowatt hours. Electron volts, we'll come on to that later in the electricity part. 1 electron volt is the energy required to accelerate an electron through 1 volt of potential difference. And that can be written as 1.6 times 10 to the 19 joules equals 1 electron volt. That's like a number like Avogadro's constant, you'll have to know. It's that because energy is equal to charge times the potential difference. The elementary charge of an electron is 1.6 times 10 to the 19, and as it's because it's for 1 volt potential difference, we times it by 1 to get that amount of energy from there. And that's another unit of energy we can use on the quantum and subatomic level. Kilowatt hour, you might have seen in appliances around the house in storing. A battery can store 3 kilowatt hours of charge. Not of charge, but of energy, but domestic term is of charge. Kilowatts is 1000 joules per second, and an hour is composed of 60 times 60 seconds, and that is equal to 3,600,000 joules of energy per kilowatt hour, or 3.6 times 10 to the 6 joules. And yeah, now, that's SI units, but this here can be inconvenient to write. It takes up a lot of time, and it's prone to errors. It's much easier to make an error. So we can use standard form rather than writing it like this. But that doesn't solve the problem entirely. What we use is prefixes. That's like kilometres. The unit is the metre, and the kilometre, the kilo bit, is the prefix or the prefix. That's a bad X. Means times by 1,000, so 5 kilometres is the same as 5,000 metres, because 5 times 1,000, or 5 times 10 to the 3 metres. Now, as you can see out of these, that's a bad K. This one is much simpler to write, much easier, much less prone to errors, and that's why we use prefixes. Now, there is a whole table of them, but there is some you have to learn for A-level. These include capital T, which stands for tera, which is 10 to the power of 12. There is giga, which is 10 to the power of 9, that's big G. Capital M is mega, which is 10 to the 6. Kilo, which is lowercase k, that's kilo, and that's 10 to the 3. And then we've got just your standard like metre. We've got centi in small c, which is 10 to the minus 2. Small m is milli, which is 10 to the minus 3. We got micro, that's this symbol here. That's the symbol, that's the Greek letter mu. We already have m and n, so we use mu. That's 10 to the minus 6. Small n is nano, which is 10 to the minus 9. P is pico, which is 10 to the minus 12. You may have seen that as measuring the size of DNA. And then I've got femto, which is 10 to the minus 15, and that's like the size of atoms. So if we apply these to up here, we can write 3.6 times 10 to the 6 joules of energy. But something that's more appropriate to write and much simpler, less prone to errors, is 3.6 megajoules. It's just much simpler. It's a bit harder here if we're using just these, because we've only got 10 to the 15. So we'll have to write 1.6 times 10 to the minus 4 femtojoules. But that is still simpler and takes less time, less prone to errors. And that's why we use prefixes. Anyway, that concludes today's video. Hope you learned something. Goodbye.